For most of human history, our technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks evolved into power plants and nuclear weapons, the biggest upgrade has happened to our brains, specifically, the machines that augment them. Since the 1960s, computing power has grown exponentially, allowing computers to become smaller and more powerful simultaneously. However, this progress is nearing its physical limits, as computer components approach the atomic scale. The challenge of miniaturization. To understand this problem, we need to grasp some basics. A computer consists of simple components that represent, process, and control data. Computer chips contain modules, which contain logic gates, which contain transistors, the fundamental switches of computing. Transistors control the flow of electrical signals, representing binary values, zeros and ones, that form the basis of all computations. Logic gates, built from transistors, perform basic operations like AND, OR, and NOT. These gates combine to form more complex modules capable of arithmetic, and from there, anything can be computed. In essence, a computer is like a group of 7-year-olds solving basic math problems scaled up. They can compute everything from astrophysics to video games. However, as transistors shrink today, reaching around 14 nanometers, smaller than a virus, quantum effects start interfering. One major issue is quantum tunneling, where electrons bypass blocked paths unpredictably, making classical computing unreliable at this scale. To overcome this, scientists are developing quantum computers, which harness the very quantum effects that disrupt traditional computing. How quantum computers work. Classical computers use bits, zeros and ones, while quantum computers use qubits, quantum systems that can be in superposition, meaning they exist in multiple states simultaneously. A qubit can be any two-level quantum system, such as an electron spin or a photon polarization. In superposition, a qubit doesn't hold just a single value 0 or 1 but a mixture of both. However, when measured, it collapses into one of these definite states. This ability to hold multiple states at once enables quantum computers to process vast amounts of information simultaneously. Another crucial property is entanglement, a phenomenon where qubits become interconnected. Changing the state of one qubit instantly affects its entangled partner, regardless of distance. This allows quantum computers to perform computations in parallel rather than sequentially. Why quantum computing matters? Quantum computing has the potential to revolutionize certain fields by offering exponential speed improvements over classical computers. Key areas include: 1. Database searching. A quantum computer can search large databases exponentially faster by leveraging quantum parallelism. 2. Cryptography. Today's encryption relies on problems too complex for classical computers to solve within a reasonable time frame. A sufficiently powerful quantum computer, however, could break modern encryption effortlessly, reshaping cybersecurity. 3. Simulations. Simulating quantum systems is computationally expensive for classical computers. Quantum computers, operating under quantum principles, could simulate molecules and proteins with unprecedented accuracy, potentially revolutionizing medicine and materials science. The future of quantum computing. While quantum computers want to replace classical computers for everyday tasks, they hold immense potential for specialized applications. Whether they become a niche tool or spark a technological revolution remains uncertain, but one thing is clear: we're only beginning to explore the true limits of computing. Dear listener, please like, share and subscribe my channel. Thanks.